Hello, everyone. Welcome to today's presentation. If you haven't attended any of our previous coffee break series, this is the second of 3 within the dynamic analysis and SRAM coffee break series. The previous one was talking about unstressed vibration analysis. Today, we're going to be talking about response spectrum analysis and some of the aspects around that involving SRAM. I wanted to start with the introductions. So for those of you that might recognize my voice, my name is Matthew Sauer. I've been doing these types of webinars for quite a while now. Today I'm joined by Tyan Aguilar. He's joining us today and he's going to be doing the demo portion of today's presentation. Andreas, who you would have heard from doing the demo last week, he's going to be doing the Q&A. Now for the topic itself, again, we're going to be talking about response spectrum analysis. It is meant to be a fairly brief and concise presentation today, so we're not going to do any deep dives because we do have other material that we're going to point you to at the end, but we wanted to just cover this topic in a little bit more detail since we have had a lot of questions about it in the last few months. So we're going to give a bit of a brief background as to what response spectrum analysis is, what it's used for, how you can run that type of analysis and interpret the results, and also talk a little bit about the equivalent static or lateral force procedures depending on where it is that you're located. They might give it a different name. So with that, let's just jump into the background on response spectrum analysis. Again, I just want to highlight that we won't be going into too much detail today because these coffee break series are meant to be short, bite-sized bits of information that can kind of open up more opportunities to learn more. But if I can break this down and boil it down into a fairly concise set of slides, I would say that, well, the response spectrum analysis uses the response spectrum, and that response spectrum curve is effectively just a relationship between the structure's dynamic characteristics. In this case here, we're talking about the period of vibration, as you can see in that plot, and the acceleration the structure would experience due to that type of shaking. So really, the response spectrum is used to estimate the maximum response of a system to certain ground motion to provide you, the engineer, with a set of possible forces and deformations under earthquake load. Now, this can be very accurate for single degree of freedom structures and as well for multi-degree of freedom systems as well. However, when you do have multiple degrees of freedom, you will have multiple mode shapes, and this approach uses a technique to basically combine the different mode shapes into one usable set. And there are some nuances that come with that and perhaps some downsides with that as well. So the combination of multiple modes is actually imperative to capture the total dynamic response of the model, because you may not necessarily have 100% mass participation in your first or most dominant mode. So the methods used for this will actually prevent the RSA method from being used for things like nonlinear elements where you might have tension or compression, because the combination methods for these different modes are going to lead to a loss of, for example, negative and positive signs when calculating nodal displacements or axial loads. So it's harder for the software to determine whether or not a node is, or a member is in compression or tension. If you have tension-only members, that sort of thing won't really jive nicely with this type of approach. That's just a downside of the RSA method. Now, there are some ways around it that we'll talk about more in the training course that I'm going to link at the end. Now, we talked a bit about the RSA curve, but whereabouts does this come from? Well, the source is really from the design code in Canada, where I'm based. The Seismic hazard calculator is available online, and it's as simple as entering your location coordinates, some soil parameters, and essentially what you get out of that is a number of different spectral accelerations at different periods. And the response spectrum, again, is determined from that spectral acceleration data. And depending on the version of the codes that you're using, there has been modifications to the Canadian code for those of you in Canada. In recent versions, they don't look at site coefficients the same way they did before, but older versions would use acceleration and velocity-based site coefficients as well. So let's talk about how we actually run this type of analysis. And the nice part is that if you were already attending our last webinar on vibration analysis, a lot of the inputs are very similar to what you would see for a vibration analysis. You want to determine the number of mode shapes or eigenvalues that you're going to extract from the model in order to accurately represent the dynamic characteristics of the structure. So that means that you're not just requesting one mode shape because that's the easiest thing to do, it solves fastest. You want to make sure that you capture enough that you're going to represent a decent portion of the structure's mass participating. And most design codes that I'm familiar with will recommend around 90% as a minimum. So if you were to add up all of the different modes and their mode or their mass participation in each axis, it would be about 90%. And they give you options as well to scale the results. So you can scale to a design code or a user-based or user-defined base shear if that's something that you wanted to do. So when we run the analysis, we're going to get a set of results, and we have to understand that as well. And something perhaps unique about this type of analysis compared to others is its ability to provide results in both a modal or a combined basis. We talked a little bit about the modal combinations. So basically how you're going to be able to combine these different eigenvalues or modes together to get a usable set. You can look at the results on a combined basis or a modal basis. And remember that the modal combination method will lead to the loss of those positive and negative signs for the joint displacements. So that does come with its downsides of not being able to necessarily get a good read of the axial loads and joint displacements, at least in terms of the directions. You'll have the magnitudes. You can also get things like base shears and overturning moments and story by story results as well. So that can be things like deflections relative to the story above or below, so interstory drifts, story forces, and even torsional sensitivity can be reported. We also have the option to run an equivalent static or lateral force procedure. There are some stipulations to when this can be run, so I recommend consulting with your local design code if you're unsure. That can certainly point you in the right direction. And this approach is, I would say, more suitable for design forces and load combinations due to the forces all being in static equilibrium. So it's essentially a simple approximation to seismic analysis using linear elastic. And the nice part is that you don't lose that sign. Everything, again, is in static equilibrium, so you don't have that loss of positive or negative joint deflection signs. And it's going to allow you to have the option to scale loads according to different code or user settings that you might define. It will also look at finding the lateral and torsional loads from the dominant modes in your model. So it can identify the dominant modes, those that have the greatest mass participation, and extract those lateral and torsional loads from there. And it will assign those loads to each floor in proportion to the active mass on that floor. And it's going to scale those displacements according to the code requirements as well. So again, this is perhaps a more suitable approach for design forces that you might want to use with, for example, nonlinear analysis, where you need those results to be in static equilibrium to gather the relative joint displacements between objects that might dictate whether a member is in compression or tension. That's just one example, but it does give you a bit more options there. So perhaps to give this a little bit more context, we can turn it over to Tyann, who is going to be presenting the demonstration for this model. So Tyann, do you mind just sharing your screen and checking the audio to make sure we've got you all set up?
Yes, Matt, thank you. Can you hear me okay?
Yes, loud and clear.
Excellent, thanks.
Let me make you the presenter as well. Give me 1 second.
Thank you. So you should be able to see my screen now, right?
Not yet. I don't see it yet.
Okay.
I think I can see it. Sorry.
Yeah, I mean, it's giving me the indication here that it's already been shared.
There we go. Okay, I can see it now.
Okay, good. So it says that the audience view is still loading, but yeah, most of you should already be seeing my screen. Thanks, Matt. And well, for those of you who already see the screen, we have here open a model that we have ready and prepared for this. Here we have a 10-story building, which has a core made of concrete, as you can see here. And we have these concrete shell elements in the core. We also have the rigid diaphragms for our slabs, as you can see in green. And we also have some concentrical brace frames around the perimeter. So we're going to be working with this model for this demo. The first thing that we want to do is to create a load case in order to analyze this. So we're going to go to the loads window and then into the create new load case. We're going to create the RSA on the X direction load case. Of course, we can also create one for the Y direction, but for the sake of time, we're just going to be focusing on the X axis for this particular demo. After we have done this, we will go to the response spectrum tool over here in the loads tool window. We're going to right click on it. And from here, we are going to click on the chart button down here. This will open the response spectrum curve dialog. And from here, we have different options. You can input the values if you have them already. But today, we're going to go to the codes button. And here we can select the code parameters that we want for our RSA curve. For the sake of this one, we are going to keep the default values in the National Building Code of Canada and the 2020 iteration. So I'm just going to click here on generate. And as you can see here, we already have the values for it. I'm going to introduce a curve name. I'm going to leave it as it is. And after this, I'm just going to click on OK. It's going to ask me to save the changes. And I'm just going to say where I want to save this into my machine. And I'm going to click on OK. After this, we have different plotting options. As you can see here in the Choose Spectra Design Curves, you have different options for this. And in order to keep a more familiar RSA curve style, I want to keep these as they are in the X and Y axis. I'm going to keep them in linear. And for the Y title, I'm going to keep it in acceleration. Please have in mind that these could show different at the beginning of your curve, but you can always set it up as you wish. Additionally, here in the choose factors and combination method, you can select which modal combination and spatial combination methods you will have. If you want more information on any of these particular methods, you can go into the help system or go into the dynamic course that we have available for you. For the sake of time, we're going to keep this as it is, and just going to go to the X scale factor and keep it at 1.0. And I'm going to introduce a critical damping radio of 0.05. After I've done this, I'm going to click on OK. And as you can see, this load case has been created and our load has been added. Now we want to run an analysis, the unstressed response spectrum analysis, and click on OK. You can have different parameters inputted there, but like Matt already mentioned, these input values are similar to the vibration analysis that we ran the last week. It's also important to remember that we request enough eigenvalues to capture a significant chunk, more than 90% of our model's dynamic characteristics. So we got a clean run now, no warning messages or anything. So after this, we can visualize the graphical results. So I'm going to go to the mode shapes tool over here. And as you can see, we have generated the different mode shapes periods for this structure. If we click here, we can see the deflection on this mode shape. And if you click on any of the other mode shapes, you will also see their scaled deflection. This is easily verifiable if you go to the numerical results window And something that is very important when we are doing dynamic analysis is to check the frequency, right? So here in the frequency spreadsheet, we can see the natural frequency that we have, and also an important data, which is the mass participation factor on each of these mode shapes, right? So we can see that the first mode shape has a high participation value on the x axis, on the x direction, but low participations, or well, non-participation on the second and the third mode shapes, right? So if we jump back into the graphical results window, now we can see, for example, the deflections on these load cases. And just like Matt was mentioning during the presentation, we have two ways of visualizing these results. The model response view, which is what I am going to highlight here. If we have the mode shape 1, we see this deflection, right? And if we click on, if we select, for example, the second mode shape over here, we see that there are no reflection, no reactions, because our mass participation factor in the second and the third mode shapes is none, right? But if we go, for example, to the fourth mode shape, we will have, once again, a different participation for these deflections. The same applies, for example, to our reactions. If we select mode shape number 1 or mode shape number 4, we see these reactions. But if we go to mode shape number 2, that has no participation factor, we have no reactions as it is expected. You can always toggle on and off this model response button to see the different mode shapes or the sum of all of our results, right? Next, I want to showcase the action force diagrams that we have here. And please note that these are all in tension due to the fact that the RSA model combination method squares our model results into a usable set, losing the sign. As Matt mentioned, there are some ways around this, but this is a byproduct of the RSA method. Additionally, if we go to the numerical results one more time, and now we click into the Interstory joint drift spreadsheet, we will be able to see how much of a drift we are having on each story. If we go to the number 1, or if we go to the number 2, we see that it goes from 19.4 to 26.37. And the higher you go up into your stories, the more drift it will have, as it is expected. As with many of the other tools that we have shown, this can be toggled into the model response type or the sum of all of our types, right? Now, the last part of these loads is how do we use this into our design workflow, right? So if we go to the loads or the geometry window, we can go to edit and generate equivalent static loads from RSA case. And we can extract all of our loads, lateral and torsional, to create new load cases. I click on OK. And as you can see here, we have created 2 new cases, the lateral force plus torsion and the lateral force minus torsion. As you can see here, I'm going to select the second load case and I'm going to toggle in my joint loads. These joint loads are here into the concrete core, and they are not shown in the RSA load case as it is expected. But we have them here on our newly generated load cases. What I'm going to do next is that I am going to deactivate my RSA load case. I'm going to switch into the loads spreadsheet. And in this load case, I'm going to click on no in order to deactivate it. After this is done, I'm going to run another analysis, this time a linear static analysis. Click on OK. I save my changes. And as you can see, this is a much quicker analysis, still getting a clean one in here. And we can verify, if we go to the graphical results window, that we have these similar deflection values, but now into an static load case. We have here our deflection values. We also have here our reaction that were generated, and important to showcase our extra loads that, as you can see now, we have positive and negative values. They are not all in tension because the equivalent static force procedure doesn't require modal combination to calculate these forces in the same way as the response spectrum analysis. Sorry. So now we can combine these load cases with other load cases that we want in order to design our structure. So that's everything I have for you today. Thanks, and back to you, Matt.
Thank you, Tyann. Let me just grab the presentation control here 1 second. Okay. So thank you again, Tyann, for the demonstration. I just wanted to wrap things up with a few summarizing points. Again, the response spectrum analysis is a great tool to estimate seismic response. It requires a lot less computational resources and time to come up with an estimate for something that we can't really accurately predict. So it's certainly a great method to do so. It also helps the fact that it's not running a full-time history analysis, something we'll be talking about in next week's webinar. So the analysis time is much less. If you have a larger model, that can certainly make a bigger difference in terms of how long the analysis takes to run. The one that Tyann was showing, I would say, is of medium size, although with using rigid diaphragms, it certainly does reduce the number of degrees of freedom. And so that makes things a little bit less complicated to not only run the analysis, but also to actually troubleshoot the results. And it's not too hard for us to then extract those equivalent static loads and perform further analysis or design checks on the model with those extracted loads, if that's something that we wanted to do. And with that, I'd like to thank everybody for their time today. We hope you enjoyed the presentation, and we look forward to seeing you in next week's webinar on time history analysis.